What if the stone that built European civilization is now its greatest vulnerability? The physics of reflectivity is failing to protect our cities, turning historic centers into vast heat traps that refuse to cool. We map albedo failure across the continent to reveal why our streets absorb heat instead of reflecting it back into space. In late June 2026, a persistent high-pressure system known as an omega block settled over Western and Central Europe. This atmospheric lid trapped hot air close to the ground, pushing street-level temperatures past 43 degrees Celsius and triggering lethal heat conditions across multiple nations. This thermal map, captured by the Sentinel-3 satellite, shows exactly how extreme this localized heating gets. During the heat wave, the dense urban core of Brussels hit 47 degrees Celsius. Meanwhile, the adjacent Sonian forest remained at a cool, stable 24.5 degrees. The reason for this 22-degree gap comes down to albedo, or surface reflectivity. Dark urban surfaces have a low albedo, meaning they absorb up to 90% of incoming solar radiation. Instead of bouncing back into space, that solar energy is retained as heat within the city blocks. The architectural identity of Europe, its iconic dark stone, dense layouts, and slate rooftops, is actively functioning as a thermodynamic trap. The built environment is weaponizing the sun against the population. To see exactly how this heat island effect operates on a micro level, we can look at the specific urban morphologies of Italian cities like Milan and Lecce. This vector grid illustrates Milan's impervious surface fraction, the percentage of land covered by sealed, non-breathable materials like asphalt and solid concrete. Because these materials lack moisture, they cannot cool through evaporation. Instead, they act as a giant heat sink, driving local temperatures up to 10 degrees higher than surrounding rural zones. This dark infrastructure was actually intentional. Centuries ago, builders used dark stone and heavy slate roofs because they were brilliantly engineered to absorb the weak winter sun, keeping interiors warm during freezing European winters. But as global temperatures rise, this ancestral survival strategy has inverted. The thermal engineering that saved these populations from freezing centuries ago is now the mechanism overheating them today. Modifying these structures presents a direct conflict with cultural heritage. Strict European preservation laws protect the aesthetic of historic districts like this one in Lecce, making it legally difficult to install modern reflective materials or cooling modifications on antique facades. These districts feature high aspect ratios, meaning buildings are tall relative to the narrow streets. This geometry creates a canyon effect, trapping infrared radiation so it continuously bounces between walls, unable to escape into the atmosphere. Above these streets sit iconic Mediterranean terracotta tiles. These materials possess exceptionally high thermal capacity, meaning they can absorb and store massive amounts of heat energy throughout the day. This creates a phenomenon known as thermal lag. Long after the sun goes down, the dense roofing material holds on to its heat and slowly radiates that stored energy downward into the living spaces below. Because of this delayed release, nighttime no longer offers biological relief. These historic homes become slow-release ovens hours after sunset. To combat this, urban planners are turning to cool pavements and high-albedo architectural materials, which are engineered specifically to reject incoming solar energy before it can be absorbed. This comparative visualization shows exactly how these materials work. On the left, standard white paint reflects visible light. On the right, newly developed ultra-white coatings increase spectral reflectance by bouncing away both visible light and near-infrared radiation. This specific chemical shift can lower localized city temperatures by up to 4 degrees. Faced with the increasing human cost of urban heating, cities like Athens and Madrid are actively testing these materials, deploying low-reflective road coatings and cooling carpets in high-traffic plazas. However, scaling these solutions is an immense logistical challenge. Resurfacing thousands of square kilometers of dark stone and asphalt across an entire continent requires massive economic investment and decades of physical labor. But modifying a city's surface chemistry is no longer an optional aesthetic upgrade. To stop the urban battery from overcharging, it is now a strict mathematical requirement. We cannot simply air condition our way out of the crisis. The heat exhausted by millions of AC units pumps directly into the streets, actively amplifying the heat island effect outside. This map illustrates the most sustainable countermeasure, increasing pervious surface fractions. By breaking up solid concrete with vegetation and highly porous reflective paths, water seeps into the ground. When that water heats up, it evaporates, naturally drawing heat away from the surface through evaporative cooling. This leaves Europe facing a choice between its historical identity and its physical survival. Can cities defined by ancient aesthetics adapt their infrastructure fast enough to function in an era of permanent heat waves? The evidence suggests that flawless preservation now comes with a measurable cost in human health. To ensure a future, the continent may have to reevaluate the materials of its past. To follow more investigations into the systems that define our modern environment, subscribe and hit the bell. We'll see you in the next deep dive into the physics and history of our world, only on Tembodocs.